Example 15.2c once again wants us to create a linear factorization for the given polynomial's equation. Now this one's a little different from part A and B simply because the degree is higher. Here we're going to see that the degree of h is equal to 4, and the linear factorization theorem would then imply that h of x is equal to a times x minus c1 times x minus c2 times x minus c3 as well as an x minus c4. Now we can find a immediately because a is that leading coefficient, which is the implied 1. So I'm going to let a be equal to 1, and now I want to look at finding the zeros for this function, but I really want to get factoring done first before I go on to that. So I'll notice that we have a trinomial, x to the 4 plus 2x squared minus 8. And this time, the power on that middle term is exactly half of the power on our leading term. So this is perfect for applying trinomial factoring. Let me go ahead and set up the two binomials. We'll have x squared times x squared, and then positive 4 and minus 2 is going to multiply to get negative 8 and add to get positive 2. So the factoring process is initiated here by trinomial factoring. But unfortunately, I can't do any other traditional factoring techniques that require me to use integers. And that's as far as I'm going to be able to take this. But it's okay because my factors here are both quadratic factors. And if they're quadratic, then I know that at the very least I can always use quadratic formula, but there may be other techniques besides that that would be available. So let me go ahead and go right into calculating the zeros. Let h of x be equal to 0, and so then we'll have 0 equals x squared plus 4, or 0 equals x squared minus 2. And that first equation will subtract 4 from both sides, giving us negative 4 equals x squared. And then I'll take the square root of both sides to get plus or minus 2i is equal to x. So that's 2 of the 4 zeros that we should be getting. And then on the second equation, I'm going to add 2 to both sides, giving me 2 equals x squared. Take the square root of both sides, and we'll have plus or minus the square root of 2 is equal to x. And there's the third and the fourth zero. Come back over here to where we let a equal 1, and let's assign the other values. C1 is going to be 2i, C2 will be negative 2i, C3 is going to be the square root of 2, and then C4 is going to be the negative square root of 2. And the order that you choose those in does not matter. They're going to end up being in their own individual factors anyway. So just whatever order you want, assign C1 through C4. And now we can write h of x as 1 times x minus 2i times x minus negative 2i times x minus the square root of 2 times x minus the negative square root of 2. And I'll clean that up just a bit. I'll drop that implied, I'll drop the 1 and make it implied. First factor is x minus 2i, followed by x plus 2i, followed by x minus the square root of 2, and then finally x plus the square root of 2. So notice that 2 of the factors have complex values in them, and the other 2 have irrational values in them. So those traditional factoring techniques that we use over and over again, like trinomial, grouping, difference of squares, those require us to use integers. So anytime we're going to have results that are irrational or complex, the only way to get that linear factorization is through the zeros. And so I'll box this in as the linear factorization for h of x.